music, what I'm about to say. Sunshine, she's here, you can take a break. I'm a hot air balloon that could go to space. With the air, like I don't care, baby, by the way.
Hi there, everybody. This is section 4.5, the next one after where we left off last week. It's about linearizations and Newton's method. This is going to look really, really familiar to you. We've been talking for quite a while about if you take a curve, take the graph of a curve, and you zoom in on a point, if it's differentiable at that point, eventually the line or the curve is going to look like a straight line. And that line would be the tangent line to the curve at that point. You've learned how to find the equation of the tangent line using a slope, the derivative, and a point. So the first part of this is really just about finding the equation of that tangent line. Okay, that is all a linearization of a function is. It's the equation of a tangent line. Now it might look a little different. But that's really all it is. F prime of A, that's just slope. F of A, that's just a point on the line. So that's kind of what those represented in the context of what we've done before. The linearizations we use to approximate values of functions that we can't easily evaluate without a calculator. So that's what one thing that they're useful for. So this is kind of so for our linearization, this first one, f of a, this point right here this is kind of a first guess to the value of the function at a point that's close to a, say maybe 0.1 above a, so it's kind of our best guess without doing anything else. Now this is the rate of change of y with respect to x, and this is kind of how much x changes. So when you multiply those together, what you get is an approximation for how much that y value changes. So if you've got an initial guess for y, and then you add to it how much y changes, what you get is an approximation for an approximate value for that function, close to this point a. You can see that here, f of x and L of x, they're close when your x value is close to a. And the farther away you get, the worse the approximation is. So let's see kind of how this works. Okay. Let's say we want to find the linearization, which we're going to call L of x, of that function, f of x, at x equals 2. Okay. Just like when you're doing the equation of a tangent line, we need two things. We need a slope and we need a point. So we've got an x value. We don't have the y value at that point. So let's go and find f of 2. That's just 2 cubed minus 2 times 2 plus 3. And let's see, 2 cubed is 8, minus 4 is 4, plus 3 is 7. So now we've got this point 2, 7 that we know is on our curve, is on f of x. Now we also need to know the slope, so we need to take the derivative. So our derivative would be 3x squared minus 2, and we need to know that derivative at this point 2, where we're writing the equation of the tangent line, or where we're writing the linearization from. So 3 times 2 squared minus 2. And that is, let's see, 2 squared is 4, times 3 is 12, minus 2 is 10. So there is our slope. So our linearization is that initial y value, which we got to be 7. That's kind of our best guess when we have an x value that's close to 2. So that's where we start. And then the slope, is how much x is changing by. times x minus the x value that we started at, too. And there is our linearization. Again, it's just the equation of the tangent line written in a little bit different fashion. Now, what can we do with that? Well, let's say we wanted to evaluate this at 2.1. We don't have a calculator handy. Okay. All of this stuff you just did in your head. Okay. So f of 2.1 is approximately L of 2.1. So we can plug in 2.1 in for x into this and get an approximate value for y when x is 2.1. So let's see what happens. We get 7 plus 10 times 2.1 minus 2. Now 2.1 minus 2, that's 0.1. 0.1 times 10 is 1. Plus that 7 is 8. So this is our approximate value for f of 2.1. Now, just for the heck of it, now if we didn't have a calculator, we wouldn't be able to do this. That is the situation where you would use it when you didn't have a calculator and you wanted to figure out what that was at a number close to 2. But let's just for the heck of it, let's see how close our approximation really was. Let's plug in 2.1 into f of x and see what we get. So it's 2.1 cubed minus 2 times 2.1 plus 3. Whoops. 2.1 cubed minus 2 times 2.1 plus 3. We got 8.061, which is pretty darn close to 8. And the closer that this point, 2.1, is to 2, the better our approximation will be. Let's try another one. Here is another function. We want to write the linearization for this function, the equation of the tangent line at x equals -4. First thing we need is the y value. So let's find f of -4. See, -4 squared is 16, plus 9 is 25, and the square root of 25 is 5. Now we need a slope. For that we need f prime. So let's see here. 1 over 2 times the square root of x squared plus 9 times chain piece, which is 2x. And we can cross those 2's out if that makes you happy. And we've got a derivative. Now we need to evaluate that derivative at -4. So we got -4 over the square root of -4 squared plus 9. We already did the bottom, didn't we? Didn't we do that up here? It was 5. So this is -4 fifths. So there's our slope. And so the linearization, our answer, the equation of that tangent line, is our kind of our first best guess for a point that's close to -4 would be 5. That is the value of the function at -4. Plus how much it changes by, which is -4 fifths, times x minus -4, but that's a plus 4. And so there's the equation of our tangent line. That's the linearization of f of x at x equals -4. And we can use that to approximate f of x at points close to -4. Again, it has to be points close to -4. The farther away you get from -4, the worse the approximation will be. So where else can we use this? Let's see another example of something we can use this for. So let's say we wanted to approximate the square root of 145. Something we might have to do in a certain situation. So what if we were going to apply this linearization stuff to it? What function do you think we'd be dealing with? Well, we're trying to take the square root of a number. So our function is the square root of x. So what we're going to do is we're going to write a linearization for f of x at some point, and it's going to help us approximate the square root of 145. So the question is, what point do we use? At what point do we do that linearization for? Because we can't take the square root of 145, not in our head anyway. So what number close to 145 could we take the square root of? Well, we could take the square root of 144. Right? The square root of 144 is 12. So that's where we're going to do the linearization, is at x equals 144. So the first thing we need to do is find f of 144, and that is 12. So really what that tells us is that this should be pretty close to 12. Maybe we could say a little more because 145 is more than 144, right? It's close to this value right here. Again, a little more. But how much more? That is the question. Next question anyway. To figure that out, we need f prime of x, which is 1 over 2 root x. And we need that derivative at 144. So that's 1 over 2 times the square root of 144. And that is 1/24. Square root of 144 is 12 times the 2 is 24. So what is our linearization? Okay, we're going to take that initial y value, 12, plus the change. It doesn't change very fast around 144. 124 is kind of a small number. And then x minus 144. So if we wanted to approximate 145, all we've got to do is evaluate this at 145. So f of 145 is approximately L of 145. So just 12 plus 1/24 times 145 minus 144. And all we're doing is plugging in 145 into that to get an approximation for the square root of 145. Now, 145 minus 144 is 1, times 1/24 is 1. So that's 12 and 1/24. And there is our approximation for the square root of 145. Which isn't bad. Now, which isn't bad, like we said. Hope that makes sense. Your assignment, let me see, where's your assignment? Oh, hold on. Your assignment for this section is page 242, number 1 through 5 and 11 through 13. Have a great day. Bye.